In this video, we are going to talk about Ethernet link aggregation, also called Ether channels. We are going to talk about link aggregation on catalyst switches. We are going to talk about supported aggregation protocols like static configuration, link aggregation control protocol, and port aggregation protocol. Then we are going to talk about load balancing algorithms. Here we are going to cover the simple protocols and the hash-based protocols. I'm going to mention a couple of things, when to use and when not to use different protocols. And finally, we are going to go through some basic configuration and troubleshooting of Ether channel configuration on catalyst switches. Ethernet link aggregation is a relatively inexpensive way to increase overall bandwidth available between two devices. These two devices can be two switches, or a switch and a router and a host, or host and a switch, or host and a host. There are really no limitations what can be done here. Of course, we are going to focus only on Ethernet link aggregation between two switches. Cisco calls link aggregation groups, lags, Ether channels. So I'm going to keep on calling them Ether channels because this is the way Cisco calls them. On catalyst switches, we can bundle up to 8 links of the same kind in an Ether channel bundle. These 8 links can be 8 fast Ethernet links, or 8 gigabit links, or 8 10 gigabit links. Depending on the protocol in use, like for example, if I were to use LACP, the Link Aggregation Control Protocol, I could bundle up to 16 links in a bundle, but only 8 of these would be active. The other 8, or if I was to bundle, say 12, the 4 additional links would be hot standby links. That means that if one of the active links in a bundle fails, one of the standby links would be able to take over and carry the traffic. Ether channels can be configured as either layer 2 or layer 3. When we configure layer 2 Ether channel bundles, all member ports, all the physical ports that are bundled need to be configured as layer 2 ports, and they need to be configured identically. That means that we cannot bundle an access port and a trunk. They need to be configured in the same way. Of course, when we configure layer 3 Ether channels, member ports shouldn't have an IP address configured, and they should be configured as layer 3 ports. We can configure that using the no switch port command. Layer 2 ports in the bundle can be either access ports or dynamic ports, or they can be statically configured as trunks. Ether channels will support ISL or .1Q. It doesn't matter. They will even support DTP. Ether channels support something that we call deterministic load balancing. Deterministic load balancing means that regardless of the load balancing mechanism in use, Ether channels will always send the same type of traffic, the same traffic belonging to the same flow over the same physical member in the link. That means if I decide to use load balancing based on, say, source MAC address, all traffic coming from this MAC address will be sent over the same physical link. There is not going to be per packet load balancing or anything of the sort. In some cases, adding Ether channels to our network will improve the overall performance. It is going to increase the available bandwidth to our hosts that are using our network. However, in some other cases, adding Ether channels will have absolutely no effect on the performance. I will talk about it a little bit later on. I will give you an example of the load balancing mechanism and the network scenario, in which case adding Ether channel will not benefit us in any way. When we configure Ether channels, we need to configure member ports. The member ports are physical ports like fast Ethernet ports or gigabit Ethernet ports that are going to be parts of the Ether channel bundle. But all logical configuration for that Ether channel needs to be performed on a logical port channel interface. For example, if we were to configure a layer 3 Ether channel, we need to configure member ports, configure the switch to use layer 3 ports in this case, and then we need to configure a port channel interface, also configure it with a no switch port command to instruct the switch that this will be a layer 3 port, and then we need to configure the IP address on the port channel interface. In many cases, this logical port channel interface is going to be automatically created for you. But in some rare circumstances, and during years of my experience when you least expect it to happen, this port channel interface will not be created. You should keep this in mind when you are configuring Ether channels to make sure that you manually configure the port channel interface. Link aggregation on Cisco switches can be, generally speaking, configured using three methods. One is to configure Ether channels statically. That means that the ports will not perform any sort of negotiation with the remote side. They are simply going to be bundled in a port channel and they are going to operate as Ether channel. In this case, we say that we have a static configuration. Cisco also called this mode on. When we have static configuration, we can have up to 8 ports in a bundle, and all these 8 ports can be active. Alternative to static configuration is using dynamic negotiation, using protocols like LACP, the Link Aggregation Control Protocol, or Port Aggregation Protocol, Cisco proprietary protocol. With LACP, which is a standards-based, we can have up to 16 links in a bundle, as I previously mentioned, but only 8 of these can be active. The negotiation of the port channel can be performed using 2 methods. One is the active negotiation, where we send LACP frames. They're called LACPDUs, which stands for Link Aggregation Control Protocol Data Units. These frames are going to attempt to negotiate with the other side the use of Ether channel, or the link aggregation group, as it is correctly called in IEEE documents. Alternative to active negotiation is the passive silent negotiation, in which case we don't send the LACPDUs. We expect to hear from the remote side before we respond. In LACP world, this is called passive mode. Port Aggregation Protocol, a Cisco proprietary protocol, operates in a very similar fashion. We have an active negotiation and we also have a silent negotiation. Unlike LACP, where these two are called active and passive, in PAGP, these are called desirable and auto. Similarly to DTP, but they should not be mistaken for DTP negotiation. With Port Aggregation Protocol, we can have up to 8 links in the bundle. Given that we have generally these 3 ways of configuring Ether channels, and for 2 of these, for LACP and PAGP, we have 2 sub-options, active, passive, desirable, and auto, we should really explore in which cases the Ether channel will form and in which cases we are not going to end up having Ether channel. So for that, we're going to head to our whiteboard and look at these different options. When we have mode on, Ether channel is unconditional. That means that whatever is configured on the other side doesn't matter. So if we have mode on one side, this is the static configuration, and we have whatever on the other side. So I'm just here going to say whatever. On the on side, the Ether channel will always be configured. What's going to be on this side here depends on what is configured on this side. If we had situation that we had on and on both sides, Ether channel will be enabled and fully functional on both sides of our link. But in a case that we had on and something else, like for example, if we had situation that we had on and active, or on and passive, or on and desirable, or on and auto, on this side of Ether channel, where we have on configured, Ether channel will be operational. But on this side where we had active, passive, desirable, or auto, where negotiation is expected, so here we expect the negotiation, Ether channel will not be functional. So we can say that from a practical perspective, in these cases here, Ether channel is not operational. So the only correct configuration here is actually to have on and on both sides. So this whatever here that I wrote, we should maybe forget about it. But keep in mind that when you are troubleshooting ether channels, for example, you may have a configuration like the one in our red box, that one side seems to operate correctly in ether channel mode and the other side is attempting negotiation and is actually failing. You have standalone, unbundled ports on the other side. So this is when it comes to static configuration with something else. But what if we had, for example, LACP configuration? Let's take a look at the possible LACP options. So we're going to examine LACP now. We have the possibility to have active and active. We also can have active and passive. And finally, we can have passive and passive. In this case, active and active, the negotiation will be successful. In the case of active and passive, the negotiation will be successful. But in a case of passive and passive, there will be no negotiation and ether channel will not form. Just as a reminder, let's take a look what happens if we have active and on, and if we have passive and on. In this case, on this side, there will be no ether channel. This side here will think we have ether channel, but in reality, this will not be functional ether channel. Finally, let's take a look at port aggregation protocol. What happens there? So when we have PEG-P, we have desirable and desirable. We can have desirable and auto. We can have auto and auto. And finally, we can have desirable and on, and we can have auto and on. In this case, ether channel will be operational. In this case, it will be operational. In this case here, it will not be operational because this is a silent negotiation. In a case of desirable and on, we are going to have ether channel operational on this side, but inoperational on this side, which means that effectively we are not going to have an ether channel working. And for the end, let's see if we have a seriously misconfigured ether channel. What happens if I have, for example, active on one side and desirable on the other side? Or if I had active and auto, and if I had desirable and passive, or if I had auto and passive. Even though these are designed to accomplish the same thing, by these I mean LACP and PEG-P, they cannot talk to each other. So in all of these cases, we are going to have inoperational ether channels. I mentioned before that load balancing in an ether channel can be performed using different algorithms. These algorithms can fit, generally speaking, into two categories: simple ones and more complex ones. The simple ones make their decision, the decision which link in an ether channel to use, based on information coming from a single source. Hash algorithms, the complex ones, use more than one source to make the determination which link in a bundle to use. I'll talk about simple and complex load balancing algorithms in just a bit. But there is this one line here on the slide that says that amount of seed bits is dependent on the physical link member count. Let me explain that a little bit. Imagine that we had a network of two switches. I'm going to call them Cat1 and Cat2. So here is my Cat1 and here is Cat2. And let's say that between these two switches, I had two links that were bundled in an ether channel. And also, I had traffic coming in this direction here. This traffic will have information like source MAC address, it will have information like destination MAC address, and if it was IP traffic, it will also have information about the source IP address and destination IP address, and it may as well have information about the source port and the destination port, in a case of TCP or UDP traffic. Now, when this traffic arrives to Ether channel, when this traffic arrives here, we need to decide which one of two links to use. Let's call these links link number 0 and link number 1. Now, no matter which algorithm we decide to use, how many bits of information from any of these values that I've shown here above do we need to make determination whether to use link 0 or link 1? Well, we have two possible options. We have 0 or 1, which means that we need only one bit of information to make this determination. How did I come up with this single bit? Well, one bit can have two possible values, 0 or 1. That means that only one bit from either a source MAC address, destination MAC address, source IP, destination IP, source or destination port, or any combination of the above needs to be used to make a determination which link to use in this case. But what if we had more than two links in our bundle? What if we had, say, 4 links in our bundle? So here I have my cat1 and cat2 interconnected using Ether channel with 4 links. Again, let's call these links 0, 1, 2, and 3. So here I have 4 possible values, which means that I need 2 bits of information to make the determination. Why? Because these are the possible values for these 4 bits. This is okay if I had, for example, 2 links in a bundle, 4 links in a bundle, or 8 links in a bundle, because all these values are powers of 2. But what if I had, say, 3 links in my bundle? What if I had a situation like this? So here I have 3 links in my bundle. This is link 0, 1, and 2. How many bits of information do I need now to sort my traffic into one of these physical links? Well, let's take a look. These are the possible values for 2 bits. So I have 4 values, but I need to use only 3 values here. But what if my algorithm chose this value here? Where will I sort this traffic? The traffic that tries to use this information. Well, as it turns out, this is a situation that you would really want to avoid, because this traffic is very likely going to end up in this bucket here, which means it is very likely going to end up in link number 1. So if you have number of links in a bundle that is not power of 2, you are risking an oversubscription of 1 or more links. This situation will happen if you have 3, 5, 6, or 7 links in a bundle. So these here are not okay. You should try to avoid this, and using 2, 4, or 8 is actually okay, because these are powers of 2. But going back to my presentation here, let's explain simple and complex load balancing algorithms a little bit. And then all those buckets and everything that I just talked about may make a little bit more sense. So let's take a look at the simple load balancing algorithms. First of all, we have to determine which traffic are we trying to load balance. Is this IP traffic or non-IP traffic? IP traffic is, of course, what we are used to call the IP traffic. Traffic that has IP addresses in IP packets. Also applies to IPv6. But in some cases, depending on the platform, depending on the catalyst switch that you are using, MPLS traffic may also be classified as IP traffic. Some switches have the ability to look beyond the MPLS headers, beyond the MPLS labels, and actually dig out the IP addresses. Some other switches don't have this capability, so MPLS traffic may be classified as non-IP or non-IPv6 traffic. For all traffic types, IP and non-IP, we always have the opportunity to use the source MAC address or the destination MAC address as the source of information for our load balancing. For IP and IPv6 traffic, we can use source IP address or a destination IP address for load balancing purposes. Let me show you that in action. Actually, not in action, but I'm going to show you in a whiteboard. Of course, I will show you all this in action a little bit later on. So let's take a look at the example that we just used here. I'm going to have two switches, CAT1 and CAT2. I'm going to have, let's say, two links between them. Very, very simple situation. And I have traffic moving in this direction here. And let's say that I want to use source IP as the basis of our load balancing. So my algorithm in use is based on the source IP address. Let's say that the source IP address here is 192.168.151.33. Which link will end up being used? Link 0 or link 1? Well, remember what I just said a little bit earlier. I need only a single bit of information here. So when we look at the IP address here, which is actually 32 bits, which bit is most likely to change? Is it the bit that determines this part of IP address or the bit that determines this part of the IP address here? Well, as it turns out, of course, it's the bit that determines this part of the IP address. And it will actually be the least significant bit in our IP address, the one that determines whether the IP address is even or odd. So if we take a look at value 3 here, written in binary, 3 is going to have value of 1, 1. Now, these are 2 bits. I don't need 2 bits, I need just 1 bit, this bit here. This bit can have 2 possible values. It can be either 0 or it can be 1. If my IP address here is even, this IP address, this bit will have value 0. If this IP address is odd, this bit will have value of 1. So we are dealing here with an odd IP address, which means that this bit will have value 1, which in turn means that I'm going to end up using link number 1. This holds true if I'm using a single bit or if I'm using multiple bits of information. So if I had the situation like in one of the previous examples where I had 2 links or 4 links or 6 links, I'm going to borrow as many bits as I need to actually use to cover all the links that I have in my bundle. Then I'm going to use the simple source of information, like in our case here, the source IP address, and then I'm going to sort the traffic in the correct bundle, or sorry, the correct physical interface. On the other hand, complex load balancing algorithms use information from multiple sources to sort the traffic into physical interfaces. Again, for all traffic, IP and non-IP, we can use the combination of source and destination MAC address for this sorting. For IP and IPv6 traffic, and remember sometimes for MPLS traffic, we can use the combination of source and destination IP addresses. On some higher-end platforms, like for example Catalyst 6500, we can actually use the port numbers as well. But this presents us with a unique problem. Let me show you what problem we are dealing with when we are using complex load balancing algorithms. Again, let's use the example of our two switches, CAT1 and CAT2. They are interconnected with two links. These two links are in an Ether channel bundle, and we have traffic arriving here, and CAT1 needs to transmit it to CAT2. Let's say that we are using the combination of source and destination IP addresses here. So I'm going to say that the load balancing mechanism in use is source destination IP. Let's say that the source IP is 192.168.151.33, and let's say that the destination IP address is 192.168.203.72. So which link are we going to use? Are we going to use link number 0 or are we going to use link number 1? Well, let's borrow these bits here. Now, you may recall from the previous example that if this IP address is odd, the last bit will be 1. And if this IP address is even, this last bit will be 0. So in this case here, we have value of 1, 0. But we need only one bit because we have only two links. If I use 2 bits here, I have 4 possible values that I'm dealing with. So how can I compress this information? How can I come up with a solution that instead of using these 2 bits, 1 and 0, in this particular case, I end up using just a single bit. So I somehow need to find a solution to use a single bit here. Well, as it turns out, I can use bitwise logical operations, like, for example, AND, or exclusive OR. So which one is the best to use in this case? Well, let's take a look at all 3 of them and make a determination for ourselves. So let's first look at AND as the logical operator. For 2 bits, I have 4 possible combinations. I have 0 and 0, I have 0 and 1, I have 1 and 0, and I have 1 and 1. The result of this logical operation 0 and 0 is going to be 0. The result of 0 and 1 is going to be 0, and 1 and 0 is going to be 0. The logical result of 1 and 1 is going to be 1, which means that if I used AND as the logical operator here, I'm going to end up with 3-to-1 load balancing ratio. This is not very good. Let's take a look at OR. Again, I have 4 possible values here, or 4 possible combinations. Let's take a look at the result of these logical operations. This is the result, 0, 1, 1, 1. Again, I have 3-to-1 load balancing ratio. I think I have to hide myself now. I need some space. Let's take a look at the result of exclusive OR as a possible solution for our load balancing problem. So again, 4 possible combinations. The difference between OR and the exclusive OR is that exclusive OR will be true if only one bit in the operation is true. So 0 XOR 0 yields 0. 0 XOR 1, we have only one bit set to 1, results with 1. So does this operation. But 1 XOR 1, where both bits are set to 1, is going to end up with 0. In this case here, I have 1-to-1 load balancing ratio, which means that AND is not a good operation, OR is not a good operation, but on the other hand, XOR is a good operation, and it will be the one that ends up being used. So these two values that I had here, 1 and 0 here, are going to be XORed so that I end up using link 0 or link 1. In this case, our result is going to be 1, because 1 XOR 0, as we can see here, yields link number 1. This means that what ends up happening is link number 1 in our bundle will be used for load balancing. Choosing which load balancing algorithm to use in your network is very important. You may recall that I mentioned that some load balancing mechanisms are good in certain cases and not so good in other cases. Ultimately, it all boils down to this. You need to know your traffic. You need to understand what is happening in your network and make a decision which load balancing mechanism to use, which load balancing algorithm to use in your network. Remember, on most Catalyst switches, the load balancing mechanism is global setting. That means you cannot configure it per interface or per logical ether channel. You can configure it only globally per box. So understanding these options is very important. I'm now going to show you a couple of scenarios and explain why certain load balancing algorithms are good in those cases and not so good in some other cases. Let's take a look at our first example. Here I'm going to have two switches, Cat1 and Cat2, connected using two links and ether channel between them. To Cat2, I'm going to have a router connected, and this router will be connected to the internet. Internet simply means a lot of hosts, a lot of IP addresses, a lot of servers, a lot of clients, whatever. It just means the big, ugly internet out there. Behind Cat1, I'm going to have a large number, or let's say relatively large number of hosts connected. So I'm just going to represent them with this box here. These devices could be directly connected to Cat1 or could be connected to other switches behind Cat1, but they are on the same broadcast domain. They are all in the same VLAN, let's say. And let's take a look at the traffic flowing in this direction here. So some of these hosts or all of these hosts are trying to communicate with the internet out there. So let's take a look at available load balancing algorithms in this case. So I'm going to have the ability to use the destination MAC or source MAC here, or destination IP or source IP. I can also use more complex algorithms like, for example, source destination MAC or source destination IP, and let's say that these are advanced switches and that I can use source destination ports as well. So which one of these algorithms here is good and which one is bad? Let's take a look at destination MAC address. So when a host behind Cat1 send traffic to Cat2, what is going to be the destination MAC address for this traffic going to the internet, remember? Well, as it turns out, it will be the MAC address of our router here, not the host on the internet, because this is what the host will see as their default gateway. This is the MAC address that default gateway is going to resolve to. This is where they need to send traffic to in order to reach the internet. So in all cases, for all traffic going from all of our hosts behind Cat1 to the internet, the destination MAC address will be a single entity, which means this is not a good choice for our load balancing. What about the source MAC address? Well, that's a good choice, because if we have a relatively large number of hosts here, the entropy is going to be big enough, so it's pretty good to use. What about the destination IP address? Hosts on the internet, end-to-end addressing? Yeah, this looks like a good idea. So does the source IP, for the same reason that we decided that the source MAC address is a good choice here. What about source destination MAC address? Well, destination MAC address will always be fixed, right? It will be the address on our router here, but the source MAC address is coming from these hosts. So this is not so bad choice, but I'm not going to mark it like this. It's okay choice. It's not the best possible one you can make, but it's okay. What about the source destination IP address? This is a good choice, and source destination port seems to be a good choice as well. But what about traffic flowing in the opposite direction? From the internet going to our hosts. Let's repeat the exercise. I'm going to put here destination MAC. I'm going to put source MAC. Let's put destination IP. Let's put source IP here, and let's write down the more complicated ones, the more complex ones. Source destination MAC, source destination IP, and source destination port. Let's take a look at this. Is the destination MAC address good load balancing algorithm to use now? Well, let's take a look. The traffic is coming from the internet, going through the router, coming to Cat2, and then going to any number of hosts here. So for traffic flowing in this direction from Cat2 to Cat1, destination MAC address is actually not so bad choice. It's a good choice. But what about the source MAC address? What will be the source MAC address of all this traffic? Well, it will be the same MAC address that we determined previously to be a bad choice. So in this case, for traffic flowing from Cat2 to Cat1, source MAC address is actually a bad choice. It was a perfectly fine choice for traffic in the opposite direction, but not so in this case. What about the destination IP or source IP? In both cases, these are good choices. Source destination MAC address, just like in previous example, it's okay choice. It's not a bad choice, not the best we can make, but it's okay. Source destination IP address, of course, it's a good choice, and source destination port is a good choice. Let's take a look at another example. So in this example here, let's have again our two switches, Cat1 and Cat2, interconnected with two links. Again, I'm running Ether channel here. Behind Cat2, I'm going to have our router, and this router is again going to be connected to the internet. But instead of large number of hosts behind Cat1, let's say that we just have a single server here. Let's take a look which load balancing algorithm is good for traffic going from server to the internet. We have the ability to use source MAC, source IP, destination MAC, destination IP. I used slightly different order than in previous example, but it doesn't matter. It's the content that matters, not the order of things. And more complex ones, I'm going to have source destination MAC, source destination IP, and finally source destination port. So let's take a look at the traffic going from server to the internet. Is it a good idea to use the source MAC address for this traffic? Let's take a look. The source MAC address for all the traffic here, no matter where it goes on the internet, will always be of our server. So this is not a good choice. What about the source IP address? What is going to be the source IP address for all of our traffic? It's going to be the server IP address. So source IP is not a good choice. What about the destination MAC address? What is going to be the destination MAC address for all of our traffic? Well, it is going to be our router here. So destination MAC address is not a good choice. What about the destination IP address? Well, large number of hosts on the internet. Destination IP address seems to be a good load balancing choice here. What about the source and destination MAC address? Well, take a look. In both cases, source and destination MAC address are the same. so this will not be a good choice. What about the source and destination IP address? Well, the destination IP address comes from a large pool of addresses, but the source IP address is a single one. So this is not a bad choice. Not the best one we can make, but it's not a bad choice. Source destination port, well, depending on the traffic here, for example, if this was a web server, our port number, our source port will always be 80. But if this is a server that performs some other duties, whatever that might be, this may not be a bad choice. So I'm just going to say here, generally speaking, this is a good choice for our load balancing. But let's take a look at the traffic going in the opposite direction. So coming from the internet and going to our server. Let me write down the options again. I'll try to use the same order now. So source MAC, source IP, destination MAC, destination IP, and here we have source destination MAC, source destination IP, and finally source destination port. Let's take a look. Is the source MAC address good choice? Well, no, because it will always be the router's address. What about the destination MAC address? Same reason, and destination IP address, which will always be the server, is not a good choice. The only good choice of the simple load balancing mechanisms here is the source IP, because this comes from a large pool on the internet. Source destination MAC address, similarly to the example above, is not a good choice. Source destination IP address is okay choice, and the source destination port seems to be a good choice in this case. So as it turns out, in almost every case, we have a load balancing algorithm that makes sense. Or is it? Let's take a look at one last example. Again, I'm going to have two switches. Cat1 connected to Cat2. And I'm going to have Ether channel between them, just like in previous examples. To Cat1, I'm going to have a server 1 connected, and to Cat2, I'm going to have a server 2 configured. And let's say that we have traffic going from Cat1 to Cat2, or from server 1 to server 2. Which load balancing algorithm is good in this case? And mind you, this applies in both directions. So I'm going to try first with destination MAC. Again, I like to change things a bit. I'm going to try destination IP. I'm going to try source MAC. I'm going to try source IP. Then the complex ones. Source, destination MAC, source, destination IP, and finally source, destination port. Let's take a look at this. If the traffic comes from server 1 and goes to server 2, which is going to be the destination MAC address for all of this traffic, it will always be server 2's MAC address, regardless of which IP addresses are in use or how many TCP sessions or UDP sessions I have between these two. So destination MAC address is not a very good choice here. What about the IP? What is going to be the destination IP address of all traffic between server 1 and server 2? Well, unless you're using multiple IPs like secondary IPs on the interfaces, in that case, the destination IP is always be the same. It will be the server 2 IP address. So destination IP address is not a good choice. What about the sources? Source MAC address or the source IP address? In both cases, not good choices. What about the combination of source and destination MAC? Look, same, same. Not good. Same applies for IP. So unless you are using a high-end switch like Catalyst 6500, there is no solution for you. Ether channel here does absolutely nothing for you. The only time where it can do something is if you're using source destination port for load balancing. keep this in mind if you're configuring Ether channels in real life. The time has come to go through the configuration examples for Ether channel. Here I have just a couple of guidelines for configuring Ether channels, the necessary steps. The first thing is configure physical port members. Make sure that the configuration on ports matches. If you are using layer 2 or layer 3, are they going to be trunks, access ports, or dynamic ports? Then you need to assign the physical members, the physical interfaces, to a port channel group. Then you can select protocol to use. Are you going to use the static Ether channel? Are you going to use LACP? Or you're going to use port aggregation protocol. Optionally, you can restrict the protocol that is in use on an Ether channel. This is using the command channel protocol on the interface. And this is actually not required for the configuration, because when you specify the channel group mode, you are going to use that protocol. This is just an additional safeguard not to use the wrong protocol on the interface. I will show you this in an example. Also, you can perform some additional protocol configuration, like port aggregation protocol or LACP parameters that you can configure per port. Then you need to configure the logical port channel interface. This will be created for you automatically in most cases, but you may remember me saying that I don't believe iOS just always. So I recommend that even though the port channel may be created for you automatically, you manually go to interface port channel with the ID that you used when you assigned groups to that port channel, and then perform necessary configuration. Make it layer 2, access, trunk or dynamic port, or make it layer 3. Don't forget, this is where you need to configure your IP address in a case of a layer 3 port channel. Optionally, you can configure several global options for Ether channel operations, like for example load balancing algorithm that you're going to use, and you can configure link aggregation control protocol system priority parameter. Enough talk. Let's go and look at some examples.